So today's video is the second in our series of acids and bases, and today's is part 1 of pH calculations. So for pH calculations, we need to be able to find and calculate the pH of different solutions. And the different solutions that you may be asked to calculate the pH of are strong acids, weak acids, water, strong bases, and buffer solutions, and we'll go over each of these in turn. So we're going to start with strong acids. So strong acids, we know, fully dissociate in solution, and by dissociate we mean that they give up hydrogen ions. So hydrochloric acid is a strong acid because in solution the reaction will go to completion, meaning that all of the acid molecules will donate their hydrogen ions to form hydrogen ions and its conjugate base in solution. And because this goes to completion, meaning there is no equilibrium, it means that the moles of acid, our moles of strong acid, is equal to the number of moles of our hydrogen ions. Because with this ratio in our completed reaction, it shows that it's a 1-to-1 ratio with our moles, but even if it's a 1-to-2 ratio with sulfuric acid, for example, it means that we can use the moles of our strong acid to find the moles of our hydrogen ions. And once we have the moles of hydrogen ions, we can use this and the volume of our solution to calculate the concentration of H+ ions, which we saw in the last video is able to be put into a pH equation to find our pH. So, for example, if we had 0.1 moles of hydrochloric acid and we mixed it in a 10 decimeter cubed solution of water, we can find the pH. So we know, because of this equation, as it goes to completion, it fully dissociates, that we also have 0.1 moles of hydrogen ions, because there is a 1-to-1 ratio between our hydrogen ions and our hydrochloric acid, and as it fully dissociates, meaning all of the acid molecules donate their hydrogen ions, we know this to be true. And then once we've found the moles of our hydrogen ions, we can put this into our concentration equation. So concentration is moles over volume. So our concentration of our hydrogen ions is 0.1 moles, which we found out from our moles of our acid, over 10, and that is because our solution is 10 decimeter cubed. Remember to keep this in decimeter cubed, so if it was centimeter cubed, you'd have to convert it, because we want our concentration to be in moles per decimeter cubed unless specifically stated otherwise. And this gives us a concentration of 0.01. And then we plug this into our pH equation, which we saw in the last video. So it's the negative log of 0.01, so the negative log of our hydrogen ion concentration, and this gives us a pH of 2. So now moving on to weak acids. So weak acids, we know, only partially dissociate in solution. So this means that only some of the acid molecules will donate their hydrogen ions to form their conjugate bases. So this means that we form an equilibrium between our acid and its dissociated products, as shown here. So Ha is our generic symbol for our weak acid, and this is in equilibrium with hydrogen ions and the conjugate base, which we call Ha. And so we don't know how far to the right this equilibrium lies. So we don't know how much of our weak acid actually dissociates into our hydrogen ions and conjugate base. So this means that we cannot work out the concentration of our H+ ions the way we did with our strong acids, because with strong acids we knew how many moles of strong acid we had, so we could work out how many moles of our hydrogen ions we had, because we knew all of the molecules dissociated. However, because we don't know how far this equilibrium lies to the right, we don't know how many of our molecules actually donate our hydrogen ions, we don't know how many moles of hydrogen ions we actually produce. So we cannot calculate the concentration of H+ ions in this way. We need to have an equilibrium constant to tell us the position of equilibrium, so then we can then work out our concentration of H+ ions. So if we put our equation back at the top there, our equilibrium constant that we need to find out our hydrogen ion concentration is called Ka, and this is the acid dissociation constant. And remember, dissociation is just the releasing of hydrogen ions in solution. So this is our Ka equation, and just like Kc, it has the concentration of our products on the top and our concentration of reactants on the bottom from this generic equation here. However, for this Ka, this acid dissociation constant, to work, we need to make some assumptions about our reaction. So if we put our acid dissociation constant at the top here and our equation, we can now go through these assumptions. So first we have to assume that the concentration of H+ ions is equal to the concentration of A- ions, so our conjugate base. And this is because for every hydrogen ion formed, we see here, an A- must be released as well. So providing there is no other source of hydrogen ions or A- ions, these must be equal. And this is because, as we see here, for every hydrogen ion that is produced, we're going to have to lose an A- as well. And we know that water does produce some hydrogen ions, and if we're dissolving our weak acid in solution, we're dissolving it in water. However, the water in the solution releases so few hydrogen ions that we can disclude it from the calculations. Water of the solution is not, and it's not counted as another source of hydrogen ions because it releases so few that it is not worth putting them into the calculation. And so, if we say that hydrogen ion concentration is equal to A- ion concentration, then we can simplify our Ka equation to, instead of having the H+ concentration times the A-, we can just have H+ squared because they are the same thing. Another assumption that we have to make is that our weak acid concentration, is constant. And this is because Ha, so our weak acid, is so weak that it only dissociates a tiny amount. Only some of these molecules, only a very few number of these weak acid molecules will actually donate hydrogen ions. So we can assume that the concentration of Ha doesn't change significantly because only some of them will actually release hydrogen ions. So hence, our acid dissociation constant, our Ka, only works for weak acids because we know with strong acids the concentration of our strong acid definitely changes because the reaction will go to completion, leaving us with no original acid left. So that is why Ka only works for weak acids, because of this assumption here. We have to assume that the concentration of our weak acid doesn't change significantly. So now we're going to look at an example. So calculate the pH of 0.02 molar per decimeter cubed solution of propanoic acid at 298 Kelvin, where propanoic acid has the Ka value of 1.34 times 10 to the minus 5 moles per decimeter cubed. So we have a specific Ka value, and this is given with a temperature because Ka is fully dependent on the temperature that the solution is at. And this makes sense because we know that a solution will dissociate more, so an acid will dissociate more in solution at higher temperatures because the molecules, the particles, have higher kinetic energy. And so it's given with a specific temperature. So we want to calculate the pH of this solution, and propanoic acid we know is a weak acid, so we are able to use our Ka equation. So first we write out our Ka equation, and we want to rearrange and input our values to find our H+ concentration. So we can then plug that in to our pH equation. So using our assumption from the previous slide, we can say that the equation is simplified to this, with H+ squared on the top. And we can input the values from the question, so our Ka value goes in there, and our concentration of our weak acid, as said in the question, is 0.02, so that can go at the bottom there. And then we want to rearrange, so we can multiply both sides by our 0.02 to get what the H+ concentration squared equals, which is this number here. And then to get our hydrogen ion concentration alone, we can square root both sides. So we get that our hydrogen ion concentration is this number here. And then we can plug this straight into our pH equation, the negative log of our hydrogen ion concentration, to get that the pH of our solution, our propanoic acid solution at 298 Kelvin, is 3.29. So we're just quickly going to look at an extension of Ka, and this is really important and does come up to trip you in questions. So it is very hard to determine anything about a weak acid from its Ka value. So we should be able to determine some things from a weak acid's Ka value about its strength. However, it's very hard to determine anything because our Ka values are such tiny numbers and have such a large range, so it's very difficult to compare them. So to make it easier to compare weak acids via these values, we use something called pKa. And pKa is the negative log of Ka. So this is the same relationship between pH and our hydrogen ion concentration. And so we do this so that we can easily compare weak acids. So if we had a Ka value of 1.5 times 10 to the minus 7, its pKa would be the negative log of this value, which is 6.82. And we can see immediately that it is not such a tiny number like our Ka value, and we know that it will have a smaller range of values. And because of this, weak acids can be better compared. So the larger the pKa value, so the larger this value here, means the smaller our Ka value, and this is because of logarithmic relationships. But you don't have to understand that. We just know that the larger the pKa value, the smaller our original Ka value actually was. And the smaller the Ka value, the weaker the acid. So a larger pKa means a weaker acid, and that is how we can compare weak acids using pKa. So pKa is just a convenience. It means that we're able to easily compare weak acids, and in questions they may give you the pKa value rather than the Ka, and you'll have to convert it to Ka to do the calculations. And to do this, you just take the negative of the pKa and you put it to an exponential.